So for introduction, the purpose of this lab is using the principles of energy conservation, the loop rule, and current conservation, which is charge conservation in steady state. We will then use those to predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure actual values of conventional current and potential differences in circuits, plus examine the behavior of ohmic resistors and capacitors. So some key concepts are Ohm's law, which is volts equals current times resistance, the loop rule, which is the sum of all delta V's equals 0, since it goes from the start and the end are usually at the same place in a loop, so then the total change in the voltage will be 0. And so by extension, there's the EMF minus IR, or how many IRs that you have for resistors equals 0. And then the node rule, which is within a node, the current I is the same as the current out, which is an Ohm's law, and the node rules are in those pictures. So for the first part of the thing, we created this circuit that you see on the right, and then what we tried to do is, based on the information given, we then tried to calculate the expected current, which my calculations are on the left. So is EMF minus IR equals 0, which then turns into EMF equals IR, and then going through that, I got 0.02 amps for current 1 and current 2, which is exactly what's pictured on the right. So my predictions were correct. And then I tried putting an ampermeter upside down, and there was no change when it was inserted upside down or backwards, as the instructions said. And then we tried to put a voltmeter, and the voltage red was the total voltage that resulted from the two batteries, since 1.5 times 2 equals 3. And then the current is read as 0 due to the fact that it is an open circuit. And so the calculations and graphs for the circuit pictured here was, so the change from AB was 3.0 volts, and then CD was negative 0.959 volts, and then EF was negative 2.0408 volts, and everything else had to equal 0 due to the fact that the total had to be 0. And then so at the bottom is my graph. And then so for the experiment, we then replace the voltmeter with an ammeter and a parallel with the 100 ohms resistors, and what happens to the current through the other ammeter is that the current turns to 0.06A, which is less current, as less current comes into contact with the 100 ohms resistor. And if you do the calculations with only the 47 ohms resistor, the current actually does end up being 0.06 amps. And so the new resistances with delta V divided by I is the 47 ohms resistor becomes 48 ohms, 100 ohms resistor becomes 102.04, and everything else still equals 0. So then we did this part with a 10 ohm bulb, a 9 volt battery, and a 200 millicapacitor. And so for the observations, at first it was very bright, but this quickly diminished as time went on. And then when we disconnected the capacitor, the bulb once again lights up, but the light seems to dim a lot slower and the capacitor charges. And then disconnecting the battery from the circuit, the bulb once again lights up, but the light seemed to dim a lot slower, just like the disconnect capacitor. But in this case, the capacitor actually discharges, and then we had to time how long it took to charge and discharge for both a 10 ohm light and then a 20 ohm light. So then it was 10 seconds to charge and 12 seconds to discharge for the 10 ohms light, and then for the 20 ohms it took 16 seconds to charge and 21 seconds to discharge. And then we did it the same thing with the 30 ohm, and then we then measured the delta V and then created this ln delta V over the initial delta V based off the equation given in the lab. And then our experimental RC actually ended up being 5.9 seconds, and then our expected RC, which is the resistance times the capacitance, was actually 6 seconds, so the values were pretty spot on. And then so for discussion, human errors are not likely. I don't know why I have it written like that in the PowerPoint, especially in the last part due to the fact that it was an idealized system on a computer. Many errors that may have occurred are then omitted, and this may explain why my values were more accurate towards the expected values, or they're very close to the expected values. And then so what if you were doing this lab in real life and use an actual ammeter instead of an ideal simulated ammeter? If I were doing this in real life, the real ammeter has resistance, which then leads to real life readings that are less than likely to be accurate as a simulation. In this case, I believe that it will actually be less than the values that I got. And what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? And how quickly would our ideal model predict the capacitor to reach full charge? And so in an ideal world, the capacitor would be charged instantly, but since this is real life and all the components in real life have resistance, there is time required to charge.